So today we're going to talk about Quaternions to Euler Angles algorithm used for a quadcopter non-degree of freedom IMU sensor. So the object of this paper is to present a method that you could get the Euler angles from the sensor. Now this is a MPU 9250 module shown that is very low cost, costs a couple US dollars, and this is the module that I'm using inside of one of my quadcopters. The object of this algorithm is to provide the three Euler angles, theta, phi, and psi. That's pitch angle, roll angle, and azimuth angle, computed from the raw data coming from a low-cost, non-degree of freedom, micro electromechanical MEMS sensor. Many low-cost, non-degree of freedom micro electromechanical sensor, such as the inertial measurement units, IMU, can provide 9 sensor parameters. They are pitch rate, roll rate, yaw rate, longitudinal acceleration, lateral acceleration, vertical acceleration, X-Earth magnetic field, Y-Earth magnetic field, and Z-Earth magnetic field. So these low-cost sensors, they provide 9 raw data outputs. They provide the angular rates, the accelerations, and the Earth's magnetic field. So it provides 9 parameters, but it doesn't provide the Euler angles. So the object of this is to find a way to get these Euler angles out of the sensor to derive it from this other data, from this raw data. Using the raw sensor data from the IMU, this paper presents an algorithm used to compute the Euler angles, theta, phi, and psi by using quaternions. Using quaternions avoids issues with singularities should multiple rotations of the vehicle occur. So there are other ways to get theta, phi, and psi, but you run into these singularities. Basically, they're like divide by zero errors that will cause the algorithm to crash. So by using quaternions, you can avoid the issues with singularities should multiple rotations occur in the vehicle. Now, if you have only a limited amount of rotation, then you could get away with the other method. But if you want to have multiple rotations, that's like greater than 360 degrees over and over again, then quaternions are the way to go. Rather than going through the theory of quaternions using Clifford algebra or geometric algebra, this paper goes into a simple practical implementation of using quaternions to provide this algorithm. The understanding of quaternions is very abstract and meaningless. There have been many other complicated methods to achieve this algorithm. However, I believe this is the simplest method. So you'll find in the public domain, you'll find many algorithms that will do this for you. Libraries you could download for Arduinos and other processors that are readily available. But they're very hard to understand, so I'm trying to provide an algorithm that's much easier to work with and understand here. So I'm going to get into how it works, and it's something that you might want to use if you're doing a little model quadcopter, a toy quadcopter. Public domain references are used to derive this algorithm as included in this paper. So I was able to search the internet and find things in the public domain that helped me with this algorithm, developing this algorithm. So all this stuff is in the public domain and free to whoever may delve in to try to use it. Complementary filters are used in this method. Quaternions are used to get short-term theta, phi, and psi, where the accelerometer is used to compute the long-term theta and phi. The compass is used to compute the long-term psi. So I decided to use complementary filters where I would have a short-term solution as computed from the quaternions and a long-term solution computed from the accelerometers for theta and phi. Now for the azimuth psi, I'm using the compass to compute the long-term parameter psi. So what you do is there's a long-term parameter, and by using the complementary filter, it kind of and the Quaternion, it kind of trims out to give you a good final solution for theta, phi, and psi. So now to go in a little bit of background information, we'll talk a little bit about the sequence of rotations used in aircraft. So we have two axes. One we would call the vehicle axis, and one would be called the body axis. So the subscript V is used for the vehicle axis, and the subscript B is used for the body axis. Now the vehicle axis is represented by this black axis, and Z always points downwards towards the center of the Earth. So this rides on the Earth, where the B axis, which we'll show down below, is attached to the airframe. So this axis is fixed relative to the Earth. This axis here would always point to maybe some direction, say north, and this axis Y would point to some direction, say east, and this axis is fixed and points downwards towards the Earth, where the body axis, which isn't shown here but we'll show it soon, is attached to the aircraft. So these coordinates xv, yv, and zv are the coordinates of this point of this axis that's on the vehicle axis. And so the first rotation, now there's a lot of different ways you could do these rotations. There's probably, I believe, 12 combinations or even more. So there's a lot of different ways of doing these rotations. But there's a standard way that was developed, kind of de facto standard used on aircraft. So we're going to use a standard axis convention that's pretty standard in aerospace industry. So the first rotation is an azimuth around psi. So that's around the z-axis. So we will do this rotation. This is a rotation matrix here. So we'll rotate at psi. That's our first rotation. So that develops the point on axis x1, y1, and z1 is the same as zv because it's rotating around that. So we develop these axes x1, y1, and z1. So if there was a point here on this axis, we could transform it into this new axis. So next is the second rotation. So we take the x1, y1, and z1 axis and then rotate it around theta, which is pitch. So we started off with xv, yv, and zv, and say xv is aligned with the nose of the aircraft, and yv is aligned with the right wing, and zv goes down through the body of the axis. So we rotated, the first rotation was around psi, around the z-axis, to x1, y1, and z1. So the next rotation is around the y1 axis in theta, and we develop a x2, y2. So the y2 is aligned with y1 and z2 axis. So now, where the nose of the aircraft used to be here, it's over here after the first rotation, and after the second rotation it's aligned with x2. So this is the next vector, the x2, y2, and z2, which is rotated from x1, y1, and z1. So the second rotation is for theta, which is pitch. So we did our first rotation, which is azimuth. Then we do our second rotation, which is pitch. And now we're going to do our third rotation, which is phi, which is the roll axis. So we did our first rotation around z and developed the x1, y1. Then we do our second rotation at theta, which is around the y1 axis, and we got x2 and z2. So now the next rotation is going to be around the x-axis, it's around the x2 axis, and it's a rotation of phi, which is roll angle. So that's going around this x2 axis. So we developed this new axis called the body axis, which is xb, yb, and zb. So now the nose of the aircraft is lined up with the xb axis shown in red. Of course, xb and x2 are the same. So now the right wing is going through the yb axis, and zb is the point going down through the body of the aircraft, pointing down, whatever you would call down relative, say, to the pilot. So we did this third rotation. So that's the sequence of rotations. The first rotation is azimuth, which is represented by psi. The second rotation is theta, which is represented by pitch. And the third rotation is phi. Roll attitude, say, bank angle, is represented by phi. So if we multiply these three matrices together in order, like you have this matrix first, this matrix second, and this matrix third, after multiplying the three rotations together, the following transformation is obtained. So we're going from the vehicle axis to the body axis. So if we take all these trig functions and put them together, this is the standard transformation going from the vehicle to the body axis. We're going through some of the preliminaries here to try to get a better understanding of how this algorithm works. So if you go to aerospace books or other references, you'll find that there is a relationship that you can find between the Euler angles and the angular body rates. So we have P, Q, and R. So these angular body rates are the raw data that comes from the IMU, the low-cost sensor. So we have this, so we could easily get these angles. This is phi, theta, and psi dot. So what we do is we integrate these. To get our Euler angles. The only problem with this is that there's singularities here. The tangent function and the secant function have singularities. So for limited rotation, this is fine. So, but if we're going to do more than one rotation, say a complete spin around, then this is going to blow up and have some issues. So it says body axis angular rates to Euler angle rates can be solved using the following equation. So we could use this to actually get this. This is actually a phi, kind of the shorthand for phi, which is the same as this phi. Okay, however, with the trigonometric functions in the matrix, such as the tangent and secant, there are singularities. Therefore, this method is limited as there are singularities. Therefore, a method using quaternions is used to avoid these singularities. Quaternions will allow multiple rotations to avoid the issues with the singularities as shown in the above equation. So this equation does work good. In the old electromechanical gyros, they had a thing called a lock. So they had gimbal lock. So they were limited to a certain point, and if you did happen to do a complete roll around, the gyro wouldn't work for a while. And eventually they had mechanisms that would trim the gyro. They would go into a lock condition for a while, and basically it would be a hard over type of sensor. But back in those days, the way flight control systems were implemented, it wasn't as big of a problem. But now we want to get more exact numbers, especially with a little quadcopter that could spin around quite a bit. So I want to show you a picture of a quadcopter I'm working on that has the MPU 9250 IMU installed, and just want to zoom out here a little bit. So this is the front of the quadcopter, where this going this direction is forward, and you can see the arms. There is a part of the propeller got cut out of the picture. This is my flight control computer, and over here this is the MPU 9250. You can see it's hidden here, but I do have the x-axis lined up in the forward direction, and my y-axis would be going out here. Actually, the y-axis is opposite, but the standard convention is to make the y-axis coming out of the right side. So I have some other sensors here. I have a Bluetooth module here to be able to talk to this, and I also have a radio control receiver that I use to be able to control this using a standard radio control transmitter. So this is the receiver. So I want to talk about the IMU MPU 9250. So that's used. There are many other ones you could purchase. They're all pretty much similar. Maybe some are better, more accurate, and less accurate, or less noisy and more noisy. I've only been using the MPU 9250, but I'd like to experiment with some of the other ones to see how they work. So anyway, we first need to take the raw data from the sensor and adjust the polarities to get them to comply with the standard aircraft axis. So previously we tried to have some background information. Now we're going to go into the guts of the standard convention, where this axis goes through the nose, the y-axis goes through the wing, and the z-axis points downward. Now that's starting in the vehicle axis, which gets transformed to the body axis. So this x-axis, xb, would be pointing with the nose, as shown in green or red, and this y-axis would be going through the right wing and the body axis, and this z-axis would be pointing downward from as the pilot would see. So this point here, the midpoint here, represents the center of gravity of the airframe. So anyway, let's go down here again, and I have a data sheet taken from the MPU 9250. So it's important to look at these data sheets to understand the polarities. So we first need to take the raw data from the sensor and adjust the polarities to get them to comply with the standard aircraft axis. Note the dot on the sheet of the device. So there's a little dot here on the chip that you can look at that helps you to reference these polarities. So in our aircraft, as shown in figure 4, this is figure 4 over here. Below, the nose of the aircraft is aligned with the x-axis. So it just so happens the way we have this oriented in our quadcopter, the nose of the aircraft, we actually have it. This is the nose of the aircraft, our forward x-axis. So our little point is right back here, is back in here. So if we go back, I'll show you where that point is. It would be like, say, down in this little corner here. So this is our x-axis. And if we go back to the first photo we saw, they actually showed it here. See, you can see the little point in here, that little dot. So this is our x, and this is our y, and z is kind of pointing into the page downward. So we're going to go back to our data sheet here. So the way this is shown, so this is our x-axis. So this would represent the nose, pointing with the nose, aligned with the nose of the aircraft. And this over here is our y-axis, which would line up, say, with the right wing of the aircraft. So that happens to be opposite of the y-axis on the sensor, and for positive polarity. So with the sensor, positive polarity, the z-axis is pointing up, but we want our polarity, our z-axis, to point down. So if we make this our x, this our y, and this our z, that would get us to line up with the standard convention used for aircraft. So that's for our accelerometers and rate gyros. So we have our P, Q, and R. That's where we want it. We want our P to be around this x-axis using the right-hand rule, and we want our Q to be around the y-axis. So pitch up, this would be pitch up going this way, would be positive, and we want our z-axis, our R, to be going around the z-axis, turning right. So that would be positive, going around the z-axis. Now for the compass, it's even different. So for the compass, magnetic field for the sensor. They, for whatever reasons, they made it different, and our x-axis is lined up with the y-axis of the magnetic field, and our y-axis, which comes out this way, is the negative x-axis, negative x-axis. But our looks like our z-axis polarity is correct for the compass. So we have to know this to adjust for this in our software to get our polarities right, to get our polarities proper. So relative to figure 4, we want the conventional standard axis polarities where forward nose is plus x, our right wing is plus y, and downward is plus z. So we want, this is what we desire. So we want roll rate right wing up. So if we're doing a right roll, we want that to be positive roll rate. And if we're going nose up, we want that to be positive pitch rate. And if we're turning right or yawing right, we want, as our nose goes right, we want that to be positive R, which is R is our yaw rate. So it has been found through experimentation that the accels are opposite to the polarity shown in the diagram of figure 4. So we actually found that our polarities appear to be opposite in acceleration. It might be like I did notice, yeah, like we do see 1g. If this accelerometer is sitting here, this is positive 1g. But I believe we want our accelerations to be opposite. We'll look at the equation some more. So accel x has the reverse polarity. So we found that this to make this positive, we have to add a minus sign. But we found that because this is opposite, we found our y-axis happens to have the correct polarity, and our z-axis has the correct polarity because these were shown in the opposite direction. So we found that the gyro x, I call this gyro x here, has the correct polarity for p, but for y and z, they have the reverse polarity. That's because they're shown opposite in opposite direction. So I'm getting into the nitty gritty here, but it's important to track this down, important to understand this because to avoid errors. So it's always good to run an experiment to verify this, and I was able to verify the polarity as shown in the documentation is correct. Relative to the gyro axis as shown in figure 4, where gyro x, gyro y, and gyro z are the raw data taken from the sensor, I have to do some adjustments. So I have to make my p is equal to gyro x is correct with no sign change, but my q and r, I have to do a sign change. So that's mostly because they're opposite to where I need them to be. And relative to the compass, I found that my I have to do some swaps here. So I found my x is equal to y, but I found my y is equal to minus x. So my y is coming out here. So that makes sense. It is equal to minus x because my y comes out here and x goes out there. And I found the z, I don't have to do any sign changes at all with z. So just want to do spelling error, fix a spelling error there. So we'll save that. And so this is what you have to do just to set that up first. So this is what you have to do to the polarities to get them right, to get them into the conventional airframe axis. So the algorithm is broken into a few parts to make it easier to compute. So part A is to compute the Euler angles theta and phi, that's pitch and roll from the accelerometer. So this is for our long-term Euler angle computation for theta and phi. So comes from STM Microelectronics document DT0058. So this is a cut and paste from that document. So step one is the computation of phi, which is the roll angle. So basically the roll angle phi is the inverse tangent of the y acceleration over the z acceleration. So that's how you compute phi. And there's some recommendations here also. Step two is the computation of theta, which is the pitch angle. And this is also from the accelerometer as previously in step one. So there's a part here they call GZ2, which is just the total acceleration vector magnitude. So the way you compute your pitch Euler angle theta, it's the inverse tangent of minus the x component of acceleration over the total acceleration magnitude. So that's from STM DT0058 Ret 3. So I also found another paper from Freescale, or NXP now. It's Freescale document number AN3461, and this is similar to what the STM Microelectronics document was. You could see the equations here that the tangent of phi is the y acceleration over the z acceleration, and likewise the pitch angle theta is the minus x component of acceleration over the squares of the y and g component, the square root of that. So this is the formula also. So I'll show you how I did it. I took these two references and came up with some equations for that on how I did it. So these are the equations I use. I first normalized the accelerometer. This is just a convenient way to handle it. So to get the x component, y, and z component, I normalize it. I take the square of each x, y, and z component, the square root of the squares of it, and take the ax acceleration divided by the total vector magnitude and the y component, and divide that by the magnitude and the z component. And this is a good way just to handle it. And note that the squares will always be equal to 1, so that's a good check to do in the software. So similar to the Freescale document AN3461, I was able to get, I call it phi A because it's phi derived from the accelerations, and theta A because it's theta derived from the acceleration. So this is the bank angle or roll angle, and this is the pitch angle. So this is from the accelerometers. So you take the inverse tangent of the y component over the z component. I took the normalized ones and take the inverse tangent of that, and that'll give you your bank angle. This would be like the long-term bank angle. And for your pitch angle, it's the inverse tangent. It's ay squared plus z squared, the square root of that, over the ax will give you that. The one thing I wanted to note is that this x component is slightly a little bit different than what's in the Freescale AN3461. If we go back to that, it shows that this is the negative. It's the negative of that, but because our polarity is reversed on the sensor, I didn't take the negative of it. So so the equations are identical to what was in that Freescale AN3461, except I didn't put the minus sign here because Rx is already reversed the way the sensor works. So now here's part C of the computations. So part C is the compute the Euler angle psi, that's the azimuth angle from data from the compass. So getting back to the STM microelectronics document DT0058, it has a step 3 in it. So it says computation of psi, yaw angle, also known as heading, based on magnometer data, Bx, By, and Bz. Units don't matter because they, as long as you use the same units for all of them. So it has some equations here. So there's a By2, a Bz2, and a Bx3. So you could see these equations here. And if you take the inverse tangent of the y over the By2 over the Bx3, that'll give you the azimuth angle. So this is what I had to do because of some polarity differences. This is my Bx, By, Bz, so I just had to negate the X compass raw data from the MP 9250. So raw magnetic field readings from the MPU 9250. So the Y is equal to the X, the magnetic field in the X direction is equal to the compass Y. The Y magnetic field is equal to the minus compass X, and the Z magnetic field is equal to compass Z. And that's because the way the chip is installed, the MPU 9250 is oriented. So similarly, I did to the accelerations, I did a similar thing where I normalized the compass readings. So I got an X norm, a Y norm, and a Z norm. And I think I used micro Tesla for the units for these, but the units don't matter. So I'm just trying to get into the algorithm. So first I compute these normalized components of the magnetic field vector, and then I computed these other factors, like it said in the document here, the DT0058. So Bz2 is equal to the Y component times the sine of phi plus the Z component times the cosine of phi. So phi and theta here in these equations is the final solution. So it's the past final solution. So in my computations, I take the past phi and the past theta and feed that back in. So you can see, yeah, the phi's here and the theta, it's the same equation. So then I compute a By2. So By2 is the Bz component times the sine of phi minus the Y component times the cosine of phi. And By3 is equal to the Bx component times the cosine of pitch angle now, plus you take this Bz2 and multiply that by the sine of the pitch angle. So I made a psi of C, meaning it's the psi that comes from the compass data. So it's the inverse tangent of By2, this is By2, over Bx3. So that'll give you your heading or your azimuth. So I believe it would be considered a magnetic heading. So that's how that would be computed. Now when I do my inverse tangent, I use a tan 2, and that avoids singularities. But since I'm just presenting the equations here, general equations, I just use the inverse tangent here. So the next part is a big part here. I call it the Q part, Compute Euler Angles from Quaternions. So referencing a paper from Diebel dated the 20th of October 2006, this is a pretty good paper that I was able to just download off the internet, and it has a lot of transformations for all different all the different combinations. Pretty big paper. So I just took a little piece out of it. So this is a paper from Diebel, and it's called Representing Attitude, Euler Angles, Unit Quaternions, and Rotation Vectors. So a relationship between the Euler angles, phi, theta, and psi, can be found in equation 290. So this is a copy out of that paper, and this is equation 290 here, and notice this is the equation for bank angle for phi, and this is the equation for theta, and this is the equation for psi. So these Q's are considered the Quaternion components. So I don't want to get into the meaning too much of Quaternions. You could investigate that further yourself. I want to go into the implementation. So I found what they call the Euler angle sequence 1, 2, 3 is the same as what we call the standard aircraft axis rotations that have been used on a lot of navigation systems for a very long time. So I zoomed here in on equation 289 and 290 because these are going to be important. I'm going to get these Quaternion components and then take the inverse tangent, inverse sine to get what to get phi, theta, and psi. And these are derived. I call these the short-term computations because they come from the Quaternions. So now I found some documentation from MathWorks that you can find in the public domain on the internet, and this is in a library for, say, an aircraft model, 6 degree of freedom aircraft model using Quaternions. But it has this nice equation here. I've seen this equation in many other books for transformations. So this is how we're going to do our Quaternion processing. So there's so we have Q0 dot, Q1 dot, Q2 dot, Q3 dot. So the derivatives is this matrix times Q0, Q1, Q2, Q3, and there's a feedback term here. What it is the squares of this are always going to be, if everything works out well in nature, is going to be equal to 1. So 1 minus 1 is 0. So there's a gain times this epsilon here. This is a feedback. This is a feedback to adjust this for some errors. But what I found is I didn't really need this in nature. If all my the way the pitch rates and roll rates and yaw rates, these are getting these Quaternions out of pitch, roll, and yaw rate. In nature, the way it works, this is always going to be a check is if you add the squares of the sum of the squares of this, it's always going to be equal to 1. So I found I didn't really need this part in my algorithm. So I just made this all 0. I made k 0 here. Although I had to experiment with it, and it does appear to work. If I set this to some gain, it does feedback and adjusts this a little bit better and provides maybe a little bit better numerical stability. But using floating point, this didn't seem to be necessary. So with P, Q, and R in radians per second, you want to make sure your body axis angular rates are radians per second. So P, Q, and R taken from the raw data of the MPU 9250, it was found through testing that epsilon was always close to 0. Therefore, the feedback path K epsilon was not required. So this represents the processing I did. So for convenience, I changed the subscripts. I did this because I've seen this done with other equations before, where instead of using Q3, Q2, Q1, and Q0, they use Q4, Q3, Q2, and Q1. So just for convenience, I incremented these subscripts. You don't have to do that, but I did it because I've had other books where they look at this Quaternions as K4, K3, K2, and K1. So the raw sensor for angular body rate polarity is adjusted for the MPU 9250 sensors. All I had to do is negate Q and R because their vectors are pointing in the opposite direction when you look at the data sheet for the MPU 9250. So P, which is roll rate, I was able to feed directly in from the gyro X, and Q I had to negate the Y axis to get that into the standard aircraft polarity scheme. And for yaw rate, this is pitch rate here, Q, and for yaw rate, is all I had to do is negate the Z axis. So I made these differential equations here. It's basically just this matrix here. So I got Q1 dot, say, equals minus P Q2 minus Q Q3 minus R Q4 over 2. Now don't get this Q over here is pitch rate, where this Q3 is a quaternion component. You don't want to get those mixed up. So anyway, these are the four differential equations that fall out of this matrix here. With this being 0 and not needed, I generated these four differential equations. So next, the short-term Euler angles are obtained from the quaternion equation. So going back to the Diable document, these come out of this equation 290 that was in that. So I call this theta q, meaning that it's the short-term Euler angles, and they are obtained from the quaternion equations. So theta, that's the pitch that is derived from the quaternions, is the inverse sine of 2 times Q2 Q4 minus 2 times Q1 Q3. So it's the inverse sine of that. And likewise for our bank angle, phi q, the inverse tangent of this will provide phi q, and psi q, which is the azimuth angle, will be the inverse tangent of this equation here. So it's just directly from what I got out of the Diable document over here. So note that the A2 tan function is used to avoid any singularities, and these are what I would call the short-term attitudes, theta, phi, and psi, where the long-term ones came from the acceleration and the compass. But they're very noisy. So what this does, gives you a nice smooth, it takes the noise out of the, if you just did it on the accelerometer and the compass, they would be very noisy and maybe not accurate. A lot of the accelerometers tend to be noisy from vibration spikes, so this will help to smooth it out. So next, you have to integrate the quaternions with the ICs shown below. So it's very important this Q1 has to I at 0 time is IC at 1, where the other ones are 0. So you take these four differential equations and then you integrate it. I like using the bilinear type of integration routine, where trapezoid rule is what I like to use. Seems to work out pretty good for when I do this in real time. So the thing is compute this Q mag, and you want to check that to make sure it's close to 1. And I always found it was always very close to 1, so I didn't need to do any adjustments or any feedback into the quaternion equation. So anyway, this will give me my my pitch angle, my roll angle, and my azimuth angle. We're heading. So the last part I have here I call part F. So use complementary filters to get a final solution for the Euler angles. So the short-term solution for the Euler angles is computed from the quaternions, while the long-term solution for the Euler angles is computed from the accelerometers and compass sensors. So complementary filters are used to mix these two solutions into one final solution. This seems to work well for the low-cost 9-degree freedom MEMS sensor, such as the MPU 9250. So basically what you do is you take your quaternion solution, which is the short term, and the accelerometer solution, which is the long term, and put this through a low pass filter. I set tau to 0.1 seconds, and this is a high pass filter. It actually washes out, and you just add the two together, and then you get a final solution. So this is the one derived from the quaternion, and this is the one derived from the accelerometer, and put it through what is called a complementary filter. So I get phi out of this. So likewise for phi, for bank angle, do the same thing. This is the long-term one from the accelerometer and the short-term one from the quaternion, and I get a final solution for phi. And likewise for psi, which is azimuth, I get one from the quaternion And one, this is from the compass, where these were accelerometers. Theta and phi came from the accelerometer. Psi comes from magnetic heading, so it's a compass solution. So I get a final solution for phi. Anyway, I was able to implement this on an STM32 microcontroller for my quadcopter, and I do it in a 32-bit floating point with the ARM Cortex M4 processor, and I use a 400 hertz update rate, and this seemed to work pretty good. I was able to get a pretty good theta, psi, and phi from a low-cost sensor like that. Believe it cost me about $4 for the sensor, so I was able to get my Euler angles out of that, and which is helpful for the control of my quadcopter. So anyway, thanks for watching this. I hope you enjoy this and have some use for this. There are many other ways of doing this. I believe the other methods you can find in the public domain are very, very complicated and take thousands and thousands of lines of code to implement, where this solution, I believe, may only be about 100 lines of code, and seem to work out pretty well. So bye now.